Hello, my name is Casey Shibler and I'm doing a reassessment video for, the Gaussian standard. I've chosen the following problem. It says, this is a picture that shows a capacitor made of two large metal plates. They're very close together and the charge is equally and oppositely distributed. As you can see, we have positive and negative charges. They're on the inner surfaces, and then we have the amounts. So for part A, it says, knowing Q, determine E. Consider a Gaussian surface in the shape of a shoebox with one end of the area A box and the interior of the left plate and the other end on the air gap. So like surface 1 right here, how it's in there and then out over here. It says, using only the fact that the electric field is expected to be horizontal everywhere in the region, use Gauss's law to determine the magnitude of the field in the air gap. Check your results that agree with earlier calculations. So what I have done is I have drawn my N just parallel to my E, so theta there is 0, and then I have my perpendicular, which is equal to 90. If I come over here, I have Gauss's law, which is the whole chapter. So E dot N dA equals the charge of the inside over epsilon naught. I actually found a problem that was similar to where I could find what the charge of the inside actually equals, and that was right here. It says the charge of the inside of the box is Q times A box over A, which is the A right here is the plate. This plate. So I plug in my values, so I now have sorry. I now solve for the perpendicular and the parallel parts of the flux going out. So I have E and dA is equal to E dA cosine theta, but this is for where it's perpendicular, so cosine theta is 90, which is 0. So we don't pay attention to that anymore. So where it's parallel, though, we have E dot NDA is equal to E dA cosine theta, which is just equal to E dA. So then I integrate, which is E dA gives me E, the integration of dA, which you can't really integrate the surface because it's not changing. So you just have EA. So then you have EA is equal to all of this, and you have Q over A of your plate times A over epsilon naught, which gives me that. So then I simplify, and that gives me E is equal to Q over A times epsilon naught. So then for part 2, it asked me to solve for surface 2, which is not touching either of the plates, it's in the middle. Basically, I like to treat this like a dipole, so I know all of the field is going towards the negative charge, whether it be on the positive end or the negative end, it's all going to be going in that direction. So, and I kind of drew it down here. So the electric field of a charged plate is equal to E times Q over A epsilon naught, which we just got. So both plates have a field going towards the negative charge, so basically that's what it's gonna be. It says in part B, to prove the electric field is constant in magnitude through the gap. That proves it right there. The electric field is going in the same direction throughout the whole thing. Nothing's really changing except for that. So therefore, the magnitude is going to remain the same. So that's the proof. Then it says, knowing Q, determine E for Gaussian box 3. Now, Gaussian box 3 is just like A. It has part of its surface in the actual capacitor ring and the other surface out. So it's going to be the same thing. It's going to be the same answer as A. E over Q, E equals Q over A epsilon naught. So then we go on to part D, and it says, using information, E fringe, determine Q. So I plugged E fringe in for E, and I have E dot NDA equals EA. So I have E fringe Q over A, 2 epsilon naught S over R. So I went ahead and set them equal to each other because we know E dot NDA, which equals EA, is also equal to Q over epsilon naught according to Gaussian's law. So you simplify everything and cancel out your variables, and you get Q over 2 times S over R equals Q.
Thank you.